Hey everyone, welcome back to Robotics. I hope you guys are doing well. Today we have our 28th lecture on robot learning. All right, so let's get started with a video. Now, this is a video of a bimanual robot that is being teleoperated. That means that there's someone off screen that's remotely controlling the robot. So for now, the robot is being guided by a human through all of these different motions. But in the future, I'd like this robot to be autonomous, to be able to do all of these different tasks by itself. So let's think back to what we learned with robot control and think about if you could design a controller to do all of these different things. I mean, to me, just the sheer variety of motion, I don't see how I can make a single PD controller that can do all the different things that you're seeing. And that motivates this video. The idea here is that a human is demonstrating all of these different tasks to the robot. The robot is recording all these different demonstrations, and it's going to try to learn a control policy by itself so it can perform these different tasks. So this theme of learning is going to be central to today's lecture. And I want to start off by first introducing what is robot learning. And then to kind of better understand those concepts, we're going to work through an example of linear regression as it applies to robot arms. All right, so let's get started. And I want to pick up with where we left off, thinking about this from a controls perspective. So in control, the robot is given a desired position, and we design a stable controller that reaches that position. So here, I've got some desired position, I've got my controller, I'm outputting torques that make my robot reach that desired position. The framework that we have when we think about learning isn't that dissimilar, but it's lifted to a higher level of abstraction. So here you can see the same overall framework, but now on the left, we've got a task. So a task is a high-level objective. Let's say, pick up the box. Over here, instead of just measuring my joint position, maybe I want to take a more encompassing measurement of the world. I'll call that my state X. Perhaps I've got camera or LiDAR also included within that observation. And again, I'll just call that my state X. My control policy is going to output actions U that are, again, kind of a higher level of abstraction. They could be joint torques, or they could be desired positions or desired velocities that I want my robot to track. And in the middle of all these things is my control policy. We often just call this a policy for short. The idea with learning is that the robot has a controller, like before, and it's got some new parameters, and we're calling those W. The robot is going to try to learn the right parameters W in order to maximize its performance for the task. So maybe putting that another way, the robot is going to be given a controller that is not fully specified by the designer. If you want to think back to what we've been discussing previously, maybe the robot is given a PID controller, but it doesn't know the right gains for that controller. So the designer is going to provide a function with parameters, and we'll call that the control policy or just policy. And the robot is going to try to tune those parameters by itself in order to maximize its performance. So let's just take a second and look at what one of these control policies could look like. Here I've got a controller, and we often call these pi. And this is going to map from states to actions. So I've got my states X and my actions U, right? And again, just like any other control law, I'm going to take in my states, my observations, and I'm going to output actions for my robot to take. And the key thing here is I've got these parameters W that I don't know, and I'm going to try to figure out what are the right parameters based on my learning process. Okay, so the key question in learning then is how do I figure out these parameters W, whether that's through experience or maybe from examples, how am I going to figure out these weights? Well, I want to walk through one example with linear regression. And this is a pretty simple example, but I think it shows a lot of the key concepts in robot learning. So for this example, the policy is going to be a linear mapping. Again, it's going to go from states to actions, but it's going to be pretty simple. It'll be what you see right here. So I'm going to output actions, and my policy is I'm just going to take my state, and I'm going to take the dot product between that state and my weights W, or the transpose, whichever way you want to describe this. So I'm going to have X transpose times W. So X is going to be a k-dimensional vector. In the past, I would have called it an n-dimensional vector, one for each link along my robot. But now, since we're thinking of this state a bit more abstractly, maybe it includes images, maybe it includes LiDAR, I'll say it's got k dimensions. So I'm going to have this k-dimensional vector. I'm just going to take the dot product between this k-dimensional vector and my k-dimensional weights, and I'm going to output a scalar action U. And here's what that process might look like. Again, I've got my action, here's my state, and here's my weights. I'm just going to take the transpose, multiply these together, and I'll get my actions. So the first step in this learning process is, again, I want to try to figure out what are these weights, but I'm going to try to figure them out based on some training data. So for each of my states X in my training set, it's going to be a labeled data set where the human is going to take a state and they're going to label it with an example of what the action should be. Maybe think back to that video we saw at the beginning of this lecture. Again, in all these different states, the human's showing me, okay, this is the action you should take at this state. So I have all my different states and I'll have actions at those states for my labeled data set. So when I see any of those states that I've already encountered, I know exactly what to do. But with learning, I want to extrapolate. So let's say there's some state I've never seen in my data set, and I mark that in yellow right here. So I've never seen this in my data set, and I want to predict what action I should take at this new state based on what I've seen in my observed states. So let's kind of aggregate all the data that I've given in my training set. So here's my first action that I've seen, and here's the first state that I saw. Again, so at this state, humans showed me, let's take this action. I'm just going to repeat that process, include all the actions I've been shown and all the different states we've visited. So let's say I record D state action pairs. What I'm going to do is I'm going to stack all D of those state action pairs. All the actions are going to form a D by 1 vector U, and all the states, when they're combined together, are going to form a D by K matrix. I'm going to call that capital X. So here, U and X, again, that's just my data set of all my state and action pairs, just aggregated together. And W is the same as before. That's my weight vector that I don't know and I want to learn through this process. Okay, so how do I learn this W? Well, in robot learning, we often design our learning algorithm to try to optimize for some performance objective. Let's say the accuracy or the error rate or the cost. And I'm going to call this objective the loss function, and I'll denote it with an L like you see right here. So I want to try to figure out what parameters are going to maximize this performance. And for this specific example of linear regression, I want to learn my weights W to minimize the total error between my predicted actions and the actions I see in my data set. So here's going to be my loss function. On the right side, these are the actions I observed. So this is the actions I should be taking. And here, X, these are the states I've seen. And X times W, that's going to give me my predicted actions. So these are the actions I think I should take, and these are the actions that we really should be taking. Ideally, I can learn W so that the predicted matches the actual. The notation here, these brackets, that means the norm or the magnitude. And the squared here, again, I'm just going to take the norm squared. So overall, this is going to be a scalar value. The lower bound will be 0 when my predicted directly matches my actual, and everywhere else will be positive. And my goal is to try to drive this down as close to 0 as possible. So I've got weights that accurately predict my actions. So there's actually a kind of a nice, clean mathematical process I can do, particularly for linear regression. So I'm going to start off with my objective. I want to find the weights W that are going to minimize my loss function. Well, if I take the gradient with respect to those weights and set it equal to 0, I can find a solution. So you might remember from geometry or perhaps algebra that if you take this gradient set equal to 0, you're finding a critical point. And in this case, that critical point will be the minimum. So the solution to equation 2 is going to minimize equation 1. And if I work through that, kind of expanding and going through this process, I end up with a nice, very clean equation for my weights. I see that, all right, the weights that are going to minimize my loss are what you see right here on the right side, the, in parentheses, X transpose X inverse times X transpose times U. So again, if you plug in what you've seen from your observed states and actions into this equation, you can output a weight vector that tells you the weights that are going to minimize your loss function. So you've learned the best weights given your data set. And here I want to illustrate what that process might look like just in some MATLAB code. So I'm going to start off on the left by collecting my data set. And this is not known to the robot, but let's say that the true value of W is what you see right here. We'll call that W star, 1, 0, 0, 0. So I'm going to have a 4-dimensional state. And in reality, the true value of that is going to be 1, 0, 0, 0. And I want to see if I can learn that value, those weights, from this process. So I've got these true weights, and next I'm going to gather my training data. I've provided a script as part of the practice set, so you can experiment with this for yourself. So I don't want to talk about it too much right now, but what I'm doing right here is I'm collecting my states and the actions that correspond to those states. And you can see I've got X times W star so that these match. And then I've added just some noise, some Gaussian noise to this process. So I've got the actions that noisily match X times W star. And then finally, I've got my states and actions. So now I want to see if I can learn the parameters W. and you see the parameters I learned right here. This equation matches what I just covered in the previous slide, and I recovered these parameters that are pretty close to W star. Again, the robot isn't supposed to know W star, that's kind of like a secret, and you can see at the end, the robot actually recovers something that pretty closely matches this unknown W star. So our learning algorithm was able to recover the right parameters based on the examples we saw. So although simplified, I think this is a great kind of capture of what we saw at the beginning of this lecture. The human's showing us different state action pairs, and I'm recovering the weights of a controller that would be able to match those examples that we saw. So that's just one example of what robot learning could be. I want to talk a little bit more about this in future lectures, but we start off by talking about what is robot learning, and we walk through this linear regression example. Before you move on to the next lecture, I encourage you to go through that practice set. You can see it in the discussion or the pinned comment. The first page has the questions and the following pages have the solutions. And then once you've done that, I encourage you to move on to the next lecture. And here we're going to think more generally about how we can learn, if we go beyond just linear regression, how we can learn more generally in these sort of robot learning contexts. So I'll look forward to seeing you there.